computer. Everybody heard that, right? All right. Okay, so this is today's activity. Well, one of three activities. We're going to start with Proton and Nmr, and we're going to do three things. No.
Okay. It's not.
It's not sharing. Everybody should have got an email with these separate. No, I guess not true. Not true. These were not emailed to everybody. Only the slides for today were emailed to everybody. Okay, so do you guys at home have the slides? Yes, no, maybe. Okay, all right. Paige does. Selena, do you have this this activity, or did I email it to the wrong thing?
I don't have it.
Okay, let me email it to you right now. New message. Send of all. There we go. Attach. There's going to be a couple Word documents like it too, so because it's going to be easier to attach that way. Attach. Come on. Activities. There it is. Oh, wrong activities, documents. There it is, NMR activities. So the PDF versions are the ones that you want. Send. They should be heading your way right now. I'll start with the instructions. Okay. So on the first thing we want to say, we want to find the number of hydrogen signals. Oops. Let's go back to here. Yeah. All right. We want to find the number of hydrogen signals for these compounds here. Then we want to calculate the number of hydrogens for each signal. And then we're going to predict the shift order. So you want to start at 0 and go to 10 and say which of these in there. So the best way to do this is to number your carbons 1, 2, 3, 4. And then you will number the hydrogens as hydrogen 1, hydrogens 2, hydrogens 3, or A, B, and C. That way you won't have to mix up your numbers. So label them A, B, C, D. Number your carbons, number your hydrogens, or letter your carbons, letter your hydrogens. And then we'll go ahead and predict the splitting for each type of hydrogen. I want you to work on this. I'm going to show you the first one, and then I want you to work on this, and we're going to go over them one by one and make sure that you have it down. Okay, so I'm going to do this first one here, and we're going to predict the number of signals first. So I'm going to start with labeling. I'm going to label this. Come on. I'm going to label this A, B, C, and D. We have that many carbons. Okay, so we're going to label our carbons. Okay. So on carbon A, are we going to have a signal? Yes. So we're going to have a signal on carbon A. Are we going to have a signal on carbon B? No, because there's no hydrogen here. But we labeled it because we're going to need to label it for carbon NMR. That's why we labeled it. Okay. So we're going to have one for C and we're going to have one for D. So we have 3 signals. Okay. So that's the first thing to do. Okay. Second thing to do is to identify the hydrogens there. So on A, how many hydrogens are we going to have? 3, because that's a methyl group, right? So we're going to have 3 hydrogens. On B, we have 0. On C, we have 2. And on D, we have 3. Okay. So that's how you do part 2. Now, part 3, you don't have to have actual things, but I want you to do a 0 and a 10. Just to have your relatives here. Which one's going to be the furthest upfield? That's closest to 0. Huh? We're not counting B because we're only looking at hydrogens. It would be D because it's the furthest away from an electron withdrawing group or electron donating group. It's the furthest away from a D shielding group. So we're going to say B, oops. We're going to say B is going to be, D is going to be right here. Okay. Now, the harder one. Between A and C, which one's going to be further downfield to your right? Left. Which one's going to be further downfield? A or C? Now, remember, when we talked about stuff being right here upfield, 3 hydrogens was further upfield than 2 hydrogens, which was further upfield than 1 hydrogen. So which is going to be further downfield? C. So we can say that C is going to be here and A is going to be right next to it, but a little bit there. Okay, so that's part 3. Now, part 4 is going to be, I want you to draw the shape of the peak. Okay, so peak A is going to be boom, boom, 1 peak because there are no hydrogens within 3 bonds. Okay. C, what shape is C going to have? This is A. What shape is C going to have? It's going to have 4 peaks because N plus 1. You get 1 peak for these hydrogens, and you have 1, 2, 3 hydrogens here. N plus 1 is equal to 4. So you can draw 4, and remember, it's going to be the 2 in the middle are going to be the same height, and the 2 next to it are the 2 on the outsides are going to be smaller. And that's the C carbon, and then the D carbon. Oh yeah, B we don't have a peak. D carbon is going to be how many peaks? 3, because we have 1 for the hydrogens plus 2, 3 for the 2 hydrogens within 3 bonds. So we're going to do 1, 2, 3. Okay, go ahead and complete the rest of the first page. I'll walk around and help you. You can work in little groups if you want. If you know somebody you want to talk through it, that's fine. Go ahead and work through B, C, and D. And what we'll do is wait, hold on. Yeah, B, C, and D. Do this exact same exercise. I'm going to walk around the room. If you want to ask questions, I'll ask your questions. I'm going to give you about 15 minutes to do this right here. This is not for grade. This is for practice. This is for practice. Ask questions. Ask your neighbor. So I'm going to start there. So around 10:30, we're going to go over the entire thing, and then we'll do the back page. And after doing this, the homework is going to be a lot easier. And homework's due Thursday night. Huh? Chapter 9 homework is due on Thursday night. Our next exam will be on chapters 7, 8, and 9. No, 8 and 9. Predominantly 8 and 9, but there will be some about 6 and 7 in there. We've got to do the synthesis now. We've got to keep adding to it. So about half of it's going to be 8 and 9, and half of it's going to be 6, 7, and sprinkle in a little 4 because we have to do some more alkane stuff too. A little more hyper than usual today. I ran a reaction overnight and it worked. And it's beautiful. Unfortunately, the reaction is so big, I have to use like blenders to get it to process right. It's soaking in 5. It's cooking in like a gallon of water. That makes 500 grams of this material. And I only need another kilo.
This material.
This material. Well, I mean, you need your aid to do it.
I did it at home, it was in my garage. I wouldn't
I wouldn't eat anything that came out. I would eat anything wrong.
Can you explain the shift order?
Okay,
one more time?
remember, think about it as the most like hydrocarbon is going to be in near zero. Okay, yeah, zero for you. Okay, it's going to be most like that. So as you get to things that are going to start to de-shield, things with electron density, they're going to pull away like double bonds. They're going to pull some of that electron density away from alkenes. And so the next thing we see is the things that are adjacent to double bonds. And the next thing we see is things that are adjacent to carbonyls. Carbonyls and double bonds are about the same place. So we're going to move from about 1 to about 2, just doing that. And then when you're next to an electron withdrawing element, oxygen or nitrogen, it's going to be a little higher. It's going to be 3, 4. That's where halogens are too. They're in the 2.5 to 3. Okay, and then the next thing up is on an alkene. And then the next thing up is on a benzene. Okay. And then the next thing up is on a carbonyl. So you have your carboxylic acids and your aldehydes. Okay. And those are about 10. So you're slowly marching down the path. Got it? Does that make sense? Because it's all about having those electrons pulled away so it can see the magnetic field. So anything that's going to pull electrons away, electronegative atoms and carbonyls, which are partially positive, are going to pull electron density away from an atom, making it de-shielded, making it walk down. This is our activity we're doing for about the next 15 minutes. And the instructions are here for only about 15 minutes. So what I would do is I would label every carbon as a ladder, and then answer the questions. And then for this one right here, I just want you to put it in relative order, starting with 0 to 10. And in this one, I want you to draw out. So if you look here, this is an example. Okay. I'm sorry, what's your name again? That's what I thought, because I have this. All right. Yeah, that's the polymer name. We'll just keep repeating and repeating. So those are benzene rings, and these are nitrogens here, and there's a positive charge, and this is counterbalancing. Explodes on contact. All right. What is it for? Oh, it's a flame resistant polymer. I'm trying to bring to market. So I'm making 1,500 grams of it. Back. And the state of Nevada is paying me to do it. So what the heck? Activity, this one. All right. Okay, you got about 20 minutes. You can ask questions. You can ask your neighbor. When you get into the test, make sure you're writing on n+1. You know what that means.
Can you go over like the peaks again?
What do you need? The
So-
peak order or the peak types?
It's fine.
Okay, so they have special names, but you have to think of one peak as a single, two peaks as a doublet, and they're going to be equal height. Okay, because you're just taking the one peak and you're splitting it into two, you're going to be equal height. Okay, now when you split it into three, you're going to have the one in the middle is going to be higher, and the other two are going to be about half height. That's called a triplet, 3 peaks triplet. Okay, when you split it into four, the two in the middle are going to be the same height, and the two on the outside are going to be the same height, a third of what the middle is. There's actually a mathematical formula that you don't have to do this, but you get the idea, and that's called a quartet, sometimes called a peak. Okay, and those are equal. And then when you got one more, you have again an odd number, so you're gonna have the one in the middle highest, the two next about half, and then these are going to be about a quarter. And that's called a pentet, 5 pentet. And then when you go to 6, it's going to be 2 in the middle, they're the same, and then 2 about half, 2 about a quarter. And that's what we call a sextet. It's 6.
And how do you know like where to assign them?
Where to assign them? Well, it's the n+1 rule. Okay, so the n+1 rule tells you that carbon A has this many hydrogens on it. That's part 1. And then carbon B, which is within 3 bonds, has this many hydrogens within 3 bonds. That's the n. And so the n+1 gives you that number. Always.
So the first A carbon is always going to be 1.
The carbon you're assigning that you're splitting is always the 1. The number of hydrogens within 3 bonds, whether it's one side or the other, is always n. Okay. So that means that if you have 1 hydrogen on this carbon, and that's the carbon you're doing, okay, that's my 1 signal, and then I can see 7 other carbons, 7 other hydrogens within 3 bonds. That's going to be 7 plus 1. It's going to be an octet. Okay, so it's always the number of hydrogens in 3 bonds plus the hydrogen you're with. You guys got any questions at home?
For C, am I looking at only having 3 signals?
Try again.
No, okay.
Either side.
It's within 3 bonds, no matter how it's connected, as long as it's through bonds.
Okay, so it can be like, I guess my question is, if it's like a really long.
So let's say this one's A and this one's B, and this one's different because it's a chiral carbon or something. There's something big here, like there's a chlorine here, hydrogen here, and then there's like this right here. So this is different than the A. Okay, so that's our 1. We have 1, 2, 3, 4, 5, 6. 1 plus 6 is equal to 7. So we're going to have a heptet. Even though one of those is only two bonds away, it's different for some reason. It's in a ring or it's something else. So you just count all of the things that you can reach within 3 bonds, 2 or 3 bonds.
It's like a range between either side.
Yeah, anywhere. If you can connect it with 3 bonds, you count it. Okay.
Thank you.
Now, yeah, and the most common way you'll see the same one attached to the same carbon is going to be in a ring. If you have a ring like this, you have this hydrogen here, and then a chlorine here, and then hydrogen here and hydrogen here. This hydrogen's different than that hydrogen because of the chlorine. So that means this hydrogen is going to split this one, and likewise. That's the most common way to have it 2 bonds. But 3 bonds is by far the most. There's no argument in 3 bonds. It's always It always counts with 3 bonds. The only time it counts with 2 bonds is there's some through space interaction. For example, alkenes, hydrogen, hydrogen, chlorine, and hydrogen. You have 3 signals because of through space. And this splits it because, come on. This splits because it's in 2 bonds. This splits because it's in 3 bonds. Okay. So 3 or less, up to 3. All right, got 5 minutes left. Everybody kind of got a good first try. Last one's tricky. Just gave you a hint. I'll look at the ring as a 3-dimensional object. Maybe that's Dr. Evil's question. Didn't go to college for, didn't go to graduate school for 4 years to be called Mr. Evil. Okay. There we go. Okay. Think through it, ask questions. Is everybody done, or you need a couple words? Couple words? All right, got 4 minutes, and then we're gonna go through them all. The Proton NMR, that polymer I showed, is horrible because all the benzene rings overlap each other. Just looks like a forest in the benzene area. You can't tell the difference between any of them. And this is long little methyl group. She's letting me use her mic. So. And she's loaning one of her students to me, but I'm recruiting my own students for that. Next semester, after grades are put in, and you want to come and do a research experience building polymers and well, come talk to me. Grades have to be in person. Can't recruit without having grades. All right, any questions at home? Got about 1 minute left, and then we're going to go over all of them, and then we're going to do the backs page too. Okay, 15 seconds. Not for grades, for practice. All right, now let's go ahead and do number B. Letter B, sorry, example B. First thing I'm going to do is going to label that A, label this B, label this C, label this D. Are we done labeling? No. So I'm going to label this one O because I said label the carbons. We label the carbons because we're going to do that in carbon NMR 2, but we're not going to label that one. We're only going to label it O. Okay, so we're going to start with going from A to O, A, B, C, D, O, to figure out our next part. So we've labeled it and we're going to find the number of signals. Okay, how many signals do we have in this compound? 5, right. A, B, there's a hydrogen on B. Don't forget hydrogen on B. C, D, and then there's the one on the O. Okay, so we have 5 signals. So that's good. We have 5 signals. All right. So let's look at how many hydrogens are in each signal. A has 3 hydrogens. B has 1 hydrogen. C has 2 hydrogens, and D has 3 hydrogens, and O has 1 hydrogen. Okay, that's pretty good. Let's start assigning right here. We're going to go do it 0 to 10 right here, which is going to be the farthest up field. D. So we're going to put D down here. Okay. Next furthest up field is going to be A. And then C close behind. And then B is going to be next. Okay. Because it's directly bonded to an oxygen, it's going to be closer to 3. The other 2 are going to be between 2 and 1, and that methyl group could be below 1, right? So we're looking at that's how far we go up. And we're not really sure where that oxygen where the hydrogen is on that oxygen because it's a broad range. And so what we're going to do is we're just going to put oh, it could be anywhere in this range. Okay. So now we have to do the hard part, the splitting. All right, so let's look at A right here. How many hydrogens are within 3 bonds of the signal for A? 1. Don't forget, there's a hydrogen on that alcohol too. There's a hydrogen right there. So it's going to be split once. 1 plus 1 is equal to 1. So we're going to have a doublet for A. B is going to be, let's see, how many hydrogens are within 3 bonds of that? We have 1, 2, 3, 4, 5, 6 hydrogens. But do we count the hydrogen on oxygen? No, you do not split through oxygen. So that means we have 1, 2, 3, 4, 5. 5 plus 1 is equal to 6. So B is going to be 6. So we're going to have a little one, a bigger one, a big one, and then the same on the other side. It's going to be symmetrical with a total of 6. Sextet. Okay. C. Okay. Let's see. C has 2 hydrogens on it, and it has 1 hydrogen with the B, 2, 3, 4 with the D. So 1 plus 4 is equal to 5. And so we're going to have a big one in the middle, and then 2 that are the same height, and then the same height here, a pentet. Okay, and then that takes us to D, which only has 2 hydrogens nearby. 2 plus 1 is equal to 3, our first triplet. And then, of course, O has a singlet because we do not split through oxygen or nitrogen. We do not split through oxygen or nitrogen. All right, questions on that? A had 1 hydrogen within 3 bonds, so it makes it a doublet. It's only the little hydrogen on B, the 1 little hydrogen on B. See, that's another reason to assign these up here. Just quickly assign them so that you can say, oh, well, A is going to be split by B, and so that's going to be 1 plus 1 is 2. And B is going to be split by C and A, so that's 5 plus 1 is 6. So you can do that. That's why I have this assigned that way. Questions? Does that make sense? All right, now it's going to get harder. All right. So how many signals do we have here? We have we're going to label our carbons. Change to blue. A, B, C, and D. And on A, we have 2 hydrogens. On B, we have 2 hydrogens. On C, we have 2 hydrogens. And on D, we have 3 hydrogens. Did everybody get that? Okay. So now let's do our, so we have 4 signals. And let's do our thing right here. Which is going to be the closest to 0? B. It's the furthest away from an electronegative atom. Okay, so B is going to be way down here. Okay, and now C and D are going to be pretty close together, with D being slightly downfield, probably upfield, sorry, because of the 3 hydrogens. And then A is going to be the furthest up. Remember, bromine is more electronegative, and therefore it's slightly higher. More electronegative. Actually, it's the same. Oh no, oxygen is more electronegative. So switch those. I think. No, that's right. That's right. Let's look at the table. Yeah, no, if you look at the table, it's right. Sorry. All right. So now let's do our splitting. Okay. So A is going to be our signal, and there are how many hydrogens on B? So 1 + 2 is equal to 3. So we're going to have a triplet. C has how many hydrogens nearby? Again, it only has B. So that's another triplet. D has 0 hydrogens within 3 bonds. So 0 + 1 is equal to 1. D. And B, how many hydrogens are within 3 bonds? 4. So it's going to be 4 + 1 is 5. So we have to draw it symmetrically. There we go. All right. Did everybody get that? All right. Now, the one that hopefully everybody got right, but we're going to start by redrawing this. All right. How many signals do we have when we redraw it? I'm going to say that all 4 of these are 1 signal because they only see hydrogens, right? They only see hydrogens through space, and the connections all the way around are the same. So I'm going to say all 4 of those are 1 signal. So that means we have this signal is A. Notice I didn't assign carbons here because we have a weird thing. So we're just going to assign signals. And A has a total of 4 carbons in it. Okay. Now, let's look at this next set here. This one's easy. This methyl group is obviously different. So we're going to call that a signal. We're going to call that B. And that B has 3 hydrogens on it. And then we're going to look at this signal here now, right here. These are different than the 2 on the top because of the methyl group. Okay. Oh, not those 2. That's wrong. Ha ha ha. We have another hydrogen back here. So it's these 2 hydrogens that are different than the 2 on the top here. So I'm going to circle the 2 on the top in purple, since I need more colors. This is a signal. Oh, and then, so that's going to be signal CD. This is signal C. And then we have one last signal here. Let's do it in orange. Right here. That hydrogen by itself is its own signal. We're going to call that E. So E has 1 hydrogen on it. C has 2 hydrogens on it. D has 2 hydrogens on it. We're not going to do splitting because they're all going to be about the same, right? They're all hydrocarbons. The only one that's going to be downfield from any of the other ones is the methyl group. The methyl group is the only thing that's different because it has 3 hydrogens on it. Everything else is going to be overlapping. So we won't be able to tell. So We don't have to do that, but now we have to do split. Okay. So let's do A first. A. Those 4 hydrogens have a single signal and they are within 4 bonds of how many hydrogens? They're within the range of the D hydrogens and they're within the range of the C hydrogens. So that's a total of 1, 2, 3, 4 for a total of 4 plus 1 is going to be a 5 peak. So we're looking at a pentet. Okay. Let's look at B. How many hydrogens are within 3 bonds of those hydrogens? Say it. 1. Don't forget. Those are hydrogens, hydrogen, and hydrogen. So that's 1 bond to get to the carbon, the other bond to get to the second carbon. And that makes this hydrogen E the only 3rd away. It's only the only one that's 3 away is 1 hydrogen. Count through the bonds. Hydrogen to carbon, carbon to carbon, carbon to hydrogen. 3 bonds. Okay. So that's going to make B a 1 plus 1 is equal to 2. A doublet. So B is a doublet. Okay. Let's do C now. How many hydrogens are within 3 bonds of C? Now remember, C is equivalent. So we're going to look at the ones that are next to one of them. Okay. Within 3 bonds of just this side. So we're going to look at this side here. How many things are within 3 bonds of that hydrogen? So we have 1 to here, 2 to the one on D, 3 to the one on A, 4 to the one on A. So we have 4 bonds within that signal. And the thing is, it's symmetrical. On the other side, it sees those same 4 ones. And so it's 1 signal seeing the same 4 hydrogens. Rings are hard. That's why we're doing a ring. So it's 1 plus 4 is equal to 5. Oh, 1 more. There we go. All right. So let's do D. Okay. So this hydrogen of C and this hydrogen of C are identical, right? So that creates 1 signal. So we only have to look at the hydrogens within one of them. Now, if we look at that hydrogen, it has 1, 2, 3, 4 hydrogens. We spin it around and look at the other one. We have the exact same position of those hydrogens. So they are splitting the other side the exact same way. So we only have 4 different hydrogens splitting that signal. The one is from E, 1 is from D, and then 2 of them are from A. Okay. So if you look at the ring this way, oops. Just too used to doing cyclohexanes. Right here, we're going to split it down here because the signal's coming from here. So it's going to be 2 here, 1 here, and 1 here. And then the other side mirrors it. So those are equivalent. So those only count twice. Okay, so that gives us our D has 1, 2, 3, 4. So it's also going to be a pentet. Okay, and that brings us to E. So E. So if we look at that, we have we're going to do that same thing. We have these 3 hydrogens from carbon B. So we have 3 plus the 1 for carbon C's and 1 for carbon D. So that's 3, 4, 5 plus 1 is equal to 6. So E is going to be, oops, 6. Okay. Aren't you glad I didn't assign this on a test? So, but I want you to work through it. See how it's symmetrical. And so that if we're only assigning 1 on the ring, we have to pay attention. Okay. but see how it's two different sides of the ring, which is why the C's and the D's are different because they're on different sides of the ring. Okay. All right. Questions at home? All right. So now let's go to the back of the page here and let's apply this. Oops. Let's go to the back page. Just looking at this right here. You can ask yourself those exact same 4 questions and even get one of them wrong and still get the correct answer. Because what we're going to say is, let's look at this. All right. How many signals is this going to have? We're going to 1, 2, 3 signals. We have 3 signals on our thing, so we're not done. How many signals is this one going to have? 3 signals. How many signals is that one going to have? 2, because it's symmetrical. That means it can't be that one. We now have a 33% chance of getting it right. How many signals are we going to have here? 4. Ooh, 50-50. All right. Now, the best way to do that is probably splitting and shift. Yeah. Okay. Signals are the unique hydrogens, right? That have see this has these hydrogens is connected to a methyl group and a carbonyl. Here, let me erase. These hydrogens are connected to a methyl group and a carbonyl. These hydrogens are connected to a methyl group and a carbonyl, so these are the same. These methyl groups are attached to this type of carbon, so these are the same. So we have 2 signals because it's symmetrical. Does that make sense now? All right. Okay. So now we have 2. So now we're going to have to play with shift or splitting. Okay. So if we look at our splitting here, we have a classical situation here. We have a methyl group, which is going to give a singlet. And we have an ethyl group that's going to give a quartet and a triplet. Oh, we had the same thing over here. We're going to get a triplet and a quartet. And then this is going to be a singlet. Well, let's look at our, maybe we got a triplet, a singlet, and a quartet. Oh, darn it. Can't do it by split. We have to do it by shift. Okay. So what we're going to see is one of the carbons is going to be attached to the oxygen, and that's going to be the furthest down field. So we need to see what the splitting is on that carbon to tell us which is closest to the oxygen. So we have a choice. If it's a carbonyl, if it's next to a carbonyl, it's going to be in the 2 range. If it's next to an oxygen, it's going to be in the 3 to 4 range. Okay, so what do we have in the 3 to 4 range? We have a quartet in the 3 to 4 range. So that means the carbon bonded to the oxygen has hydrogens that have at least 3 hydrogens within 3 bonds away. It has to be the ethyl group. So that means we have to look for the structure that has the ethyl group bonded to the oxygen, because the quartet is bonded to the oxygen because it's up above 3. So which does that mean? Is it the first one or the second one? It has to be the first one because this one is further downfield and it has to be a quartet. Does that make sense? Because this right here, the quartet would be down near 2, because things down near 2 are next to carbonyls. So we'd have a quartet near 2 and a singlet at 4. That's why I did you do the assessment on the other side, because now you can say, oh, this one's going to be higher than this one, and this is going to be a singlet. And that's not what we see. We see the quartet highest. Because the quartet's highest, you can distinguish between the 2. Does that make sense? Does that make really, I mean, that's why I love this exercise, because you're finally going, oh, gosh, I didn't do it. So, all right, let's do that again right here. Okay, and we could probably eliminate a couple of them just by signal. So let's look at that. Let's look at how many signals here. We got 1 signal, 2 signal, and then there's a hydrogen here. So we have 3 signals. And look at this. It's symmetrical again. So we only have 3 signals because of symmetry. Now, one of those signals on this one is going to be pretty high. It's going to be up near 5 because the one's on the alkene. We haven't done above 5 yet. So the alkenes are 5 and 6, benzenes are 7 and 8, right? So we're working our way down. Okay, so let's look at this one right here. How many signals are we going to, sorry, we have 3 signals here. Okay, how many signals do we have on the next one? 2. We have 3 signals in our spectrum. Can that be our compound? No, all right, yay, 33% now. Okay, now let's look at the next one. We have 1, 2, and 3. So that's possible. And this has 1, 2, and 3. Again, possible. Now I like showing this one because I want you to pay attention to symmetry, right? Because equivalent hydrogens have the equivalent connection. They're not just in this different, they can be in the different parts of the molecule. As long as they have equivalent connections, they are equivalent. All right, so we're down to 2. No, we're down to 3. Okay, can we eliminate one of these choices automatically? Let's look at our spectrum, okay? All right, we have a singlet. This looks like a quartet. This is a triplet. This is a singlet. Okay, so, all right, let's look at splitting here. This is going to be a singlet, a quartet, and a triplet. This is going to be a triplet, a quartet, and a singlet. This is going to be a triplet. This is going to be a quartet. This is going to be a singlet. This is going to be a triplet, a quartet, and a singlet. Come on. Test tapping the wrong side of the. Just going here. So this is going to be a singlet. And this is going to be a singlet, triplet. No, this is going to be a quartet, and this is going to be a triplet. Well, that didn't help. All right, let's look at shift. Okay. This one is going to have nothing above 3. No, nothing above 4 ppm. 4 ppm. Because we have this bonded here, so that's going to be around 2. We have this bonded here, it's going to be around 4. We have something at 5. What's at 5? The singlet, the ethylene, the one on the double bond. So that means it can't be that. All right. So now we're down to, what does it look like? So the singlet on both of these is going to be the one on the alkene. Okay, so now we need to pay attention to the quartet and the singlet, the triplet. If the quartet was down around 2, that would be the one bonded to the carbonene. If the quartet is around 4, it must be bonded to the oxygen. Okay, if the quartet is at 2, 2.5, it has to be bonded to the carbonyl. If the quartet is bonded to 4, it must be bonded to the oxygen. So which is our choice? The third one, right here. Oops, wrong screen. Okay. All right. So do you see how to use those 4 things that are important in carbon and proton and Nmr to not only figure out what it should look like, but be able to discern between structures? Do you like this exercise? Because it'll really help with the homework. All right, now we're going to shift gears a little bit, and we're going to go to carbon NMR. Okay, and I'm going to hand those out now. Now we're going to do exactly the same thing we did with the other one, but we have a different structure. At the end, our ring is different, so I can do something else. But we're going to label those and assign them shifts in general. But our shifts are, of course, going to be between, on all of these, they're going to be between 0 and 8. But we'll just say 100 because that's fine. All right, you have 15 minutes to do this, but let me show you how I want you to do it. Again, all we have to do is number the carbons. A, B, or letter the carbons, C, D. Don't forget your carbonyl this time because we got to use them. And predict the shift order based on how close it is to the electronegative atom or an electron-rich species. And you only get 15 minutes to do this because it is only half. You can also look back at the table for shifts just to make sure you got your shifts going on. Let's go to, oops, wrong one. Let's go to. There we go. So if you can't tell the difference between the shifts, things that kind of overlap, just put them together. Most of the time you can identify by splitting after that. About 5 more minutes. It's about 11 o'clock. So if you want to take a bio break, you can. On that side a little bit. And then at 11:05, we'll start going over this and look at the back page. Questions? Well, we're just doing carbons here. We really don't have to worry about, and this one, if you look, you have to draw it on side. So you just want to find the number of carbons. You can have students. So you're going to have fewer signals than you think you have. But you can make sure you all how about that? Is that a good hint? Camille, Jenna. All right, you guys at home done? We're about to start back up and do the answer. Done. And activity. All right. All right, last 30 seconds. Finish up. All right, let's go ahead and look at the first one. Do we care about the oxygen? Yes, only when we're talking about shift, but we don't care about it when we're talking about carbon NMR. So we have A, B, C, D. So we have 4 peaks. Okay. One peak is very different than the 3 other peaks. Which is that one? B. B is going to be further downfield. So if we were to assign these, we go, let's do 70, or no, let's do 100, because we had to do 200. Oh, sorry, let's do the one above 2. The carbonyl, of course, is going to be around above 200. Carbonyls with ketones and aldehydes are 180 to 220. Carbonyls that have oxygens, nitrogens, or OH groups on them are 170 to 185. So if they have electron-rich things, they're not as shifted as high because of back conjugation. But it's going to be right between 180 and 220 for a ketone. So that's why that's shifted so high. Then the A and C are going to be next. Probably the A is going to be closer to 0 than C because of the 3 hydrogens, and then D, of course, is going to be closest to 0. So if we look at here, we're only going to be around 70 to 80 for the one bonded directly to the oxygen. So we're going to say B is here. And then again, we'll have C and A really close together, but A is slightly down, slightly upfield because of the 3 hydrogens, followed by D. Okay. All right. So now we have to look back at our table here and look where our carbons show up here. Look at this, our OH, our OR, and our CL all show up in the same range. Okay, so we're going to have to just put them all in the same range. And so that's going to give us the activity here. So when we do our shift here, we have how many signals, first of all? We have, let's see. Come on. 1, A, B, C, and D. And it looks like A, C, and D are all going to be lumped together at around between 170 ppm. And then B is going to be not probably, maybe around 30. Okay, that's all we can tell. We don't have any splitting. We don't have any ways to tell how many hydrogens are on. All right, now let's do the last one. Now I put the ring on there again so that we would pay attention to that. And I'm going to do, let's do this one right here. So we have the carbonyls. Now let's look at the skeleton attached to the carbonyl. We go one way, we have a CH2 and then a carbonyl. We go the other way, we have a CH2, 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 then carbonyl. Okay, so if we do the same thing to the other carbonyl, they're identical because we have symmetry. So we have 1 for the carbonyls. So that's A. This is B. This is C, the one here, and then D is both of these. So A has 2 carbonyls. D has 2 CH2s. B is its own CH2 because it's between the 2 carbonyls. And C is its own CH2 because it's farthest away from the carbonyls. So we have 4 signals. Okay, so now let's rack and stack those with 0. And the carbonyls are going to be way up because they're ketones. They're going to be over 200. So we're going to have to go all the way up to 200. And we're going to say that A is probably going to be above 200. It's going to be between 180 and 220. Okay, and that's the only thing in there is aldehydes and ketones. Okay, so that's A. So what's next? As we're starting to move down, or we're starting to move upfield, we're starting to move further away from this. What's going to be next? Why? 2. It has 2 carbonyls nearby. If we look at B, that only has 1 carbonyl nearby. So that means we're going to have B, A, and C. C is the furthest away. It only sees 2 CH2s. And then it sees a carbonyl through multiple bonds. It has to go through 2 bonds before it sees the carbonyl. Here, this one has a carbonyl within 1 bond of it. So it's shifted highest. Does that make sense? Oh, A, B. This is A, this is A. This is D, this is D. So, sorry. So the carbonyl is A. So this is D. Sorry. I see what you're talking about. So yeah, D is the CH2 next to 1 carbonyl and 1 CH2. A is the carbonyl. B is the one in between the carbonyls, and C is the one furthest away from everything. Does that make sense now? that I corrected it. Thank you very much. Right. So let's use those same rules to look for these compounds. Okay. So let's see. This right here, I want to show you. That's actually the solvent. So we're not going to worry about that. And so what we're going to do is we're going to say, how many signals do we see in our spectrum? 1, 2, 3, 4, 5. So we have 5 signals. So now let's go through each of our compounds and see how many signals we have. On the first one, how many signals do we have? We have 5 in the ring. 1 signal, 2 signals, 3 signals. So can it be this compound? We have 5 signals in our spectrum, so it can't be that one. All right, let's look at this one. 1 signal, 2 signal, 3 signal, 4 signal, 5 signal, because carbonyl counts. All right. Go to the next one. 1 signal, 2 signal, 3 signal, 4 signal, 5 signal. Okay. This one's going to be hard. 1 signal, 2 signal. These are probably the same 3 signal. These are probably the same 4 signal, 5 signal. Okay. So let's look at shift then. Where is this carbonyl going to be based on shift? It's got a carbonyl with a hydrogen on it. So it's an aldehyde, and aldehydes and ketones are above 180. Okay. So where is our thing? All right, at 180. Okay. So this is a carboxylic acid. Where would our shift be for that? 170 to 185. It's actually pretty good in that range. That's a maybe. And this is a ketone. Where's it going to be? 180 to 200, 220. So I think that we are probably, well, okay, still could be, it's right on the edge. Okay, let's do some other things. Where would these peaks on the benzene show up? They're going to be 100 to 160. Do we have anything in that range? No, so we can eliminate this one. Yay, we're down to 2, 50-50. Okay, so we have to pay attention to which do we think it's going to be? So we're down to 2 choices. And it's really barely in the 180. The carboxylic acid is 170 to 185. So it's actually below the 180 that we expect the ketone to be at. So the correct answer is the carboxylic acid. What if I gave you an IR? Would you be able to tell the difference between the carbonyl and the ketone and the carboxylic acid? Yeah, that'd be a nice little thing. Or I could give you the proton. And you could see that there would be in this one, if I gave you the proton NMR also, there'd be a singlet here and there's no singlet here.
So should we memorize the general range for like functional group?
Yes. That's why those tables are there. You can use the table, the numbers table, or the image of the shift. Either one, whichever works best for you, but yes. All right, so now let's do this other one here. Oh gosh, we already looked at this. Oh, but that was proton. So we gotta. Okay, so we're gonna look for, let's see, we have it. That's 150, 160. Wow, that's barely 165. Okay. So that's probably an ester, a carboxylic acid, or an amide, or a benzene ring. Okay. We don't have any benzene rings, so I guess we don't have to worry about that. We do have a peak here at 130. So that's probably our double bond. This is probably our carbonyl with an electronegative atom. So it's going to be an oxygen or a nitrogen or a chlorine or something like that. And we have what looks like just 2 other peaks. That looks like just, so we have 4 signals. Okay. So let's see, how many signals are we going to have here? 1, 2, 3, 4. Signals here, 1, 2, 3. Ah, because of symmetry, we only have 3 signals. Let's look at this one. 1, 2, 3, 4. Don't forget your carbonyl. 1, 2, 3, 4. Okay. So just like before, we have 4 signals, but we can eliminate one more of these. Which one can we eliminate? The last one, because there's not a thing there's no double bond in here. So it's got to be, oops, wrong. Again. All right, so it's got to be one of these two. So how can we tell the difference between these two? We're going to have to go to shift, okay? In one, we have a carbon next to a carbonyl. Oh, wait, hold it. Do we have to go to shift? Yeah, we do. Where would the carbonyls on this one be? 180 to 220. Where is our shift? This is 150, 160, 165. So what's our answer? The ester. So NMR is not mysterious. It makes sense. Use the tools you have. Even if you get something wrong, you can usually find the right answer. Okay. All right. Now let's go to our last example. Our last activity here. I'm going to give you the proton and carbon NMR. You have to do a little bit of what's it called? Where you try to imagine that it's not there, so it's more fun to look at. Anyway, I accidentally answered it. But anyway, so if you pull up the last one, but we're going to talk our way through it. I want you to talk your way through it. Make sure that you identify the correct one. And then you only have 5 minutes for this example. 5 minutes for this example. And then you want to identify each of the compounds correctly. And then we'll talk through it. And we'll do that exact same thing. We'll compare the carbon to the proton and the structure. And we will get to our thing. This is going to be like a question you'll see on the next exam. This will be like a question you'll see on the final. So this is what we want you to do. We want you to use the knowledge you just gained, get as close as you can to the right answer, and then make a rational decision based on what you know. Unlike baseball, where there is crying, there's no guessing in chemistry. Make a rational choice. Make a rational choice. Oh, I have a different, oh, it's on the back page. That's why. Ha ha ha. All right, you'll have to 11:25, and then we'll talk to the rest, and that'll take us to 11:40. So that'll take us to the rest of the class. And then the slides I gave you today, we're going to work on tomorrow. It's a kind of a review of all the chemistry we have up to now, plus retrosynthetic strategy. And then we'll have, that's Thursday, so we'll, and then at the end of that, we'll have a review for the exam on Friday. Yeah, that little teeny peak there is actually, it's 3 peaks together, and it's for chloroform. It does a weird thing. So the little tiny peak in a carbon NMR, which is looks really wide, that's the solvent. So you want anything, you want it taller than 1 inch, or else it's probably not a signal.
Is it only in carbon?
Only in carbon NMR, because see how noisy the baseline is? In proton NMR is much cleaner. So even though it's less than 1 inch, that is a peak, and that's a peak. And this is our, that's our zero. That's our internal standard.
Okay.
Anything pre-med? You have study groups where you bring in something and you teach it. You need a study group. You need a study group where you divide up something into five sections. Each person teaches a part of it. Teaching a subject, you learn it better than just when you're trying to learn it. Get a study group. Helps with organic chemistry too, where you each bring in a reaction and explain the chemistry and what the regiochemistry and everything like that. We don't have time for that in the summer, but in the long semester, sure, especially the second half, when you have to remember all the stuff from the previous one. Be a good idea to have a study group, about 5 people, break it up into 5 different things. Everybody teaches something. You want to keep it down about 30 minutes. 5 minutes to present, and then 5 minutes to know. I do a thing with my research students where we bring a paper in and rip it to shreds. So we know how not to write a paper. Do that for my PhD students too. We do that in our PhD classes. All right, any questions there at home? We got about 3 minutes left, and then we're going to start talking through this. All right, about 45 seconds. Come up with an answer. I just learned my daughter's gonna be very expensive. She went to opera camp. So, she's 16. The guy from Opera San Antonio is like, we had season tickets to the Majestic for musical theater for years until COVID hit. And so my kids are very theater savvy. And so, but now opera's a whole level of expense above that. All right, let's go and look at what we have. I'm going to do it backwards now. I'm not going to look at the structures. I'm going to look at what we see first. So the first thing we see in this spectrum is 4 signals. And one of those signals is, and it is also 1. So we have a an amine or a alcohol in our first compound here. Okay, now if we look at the splitting, I mean, it definitely looks like that's a triplet because the middle's high. This is a multiplet, so we have a lot of splitting in that one. We're not really sure about this one. This one could be a singlet or a doublet, not really sure. Okay, so we have to take that into account. But we have a total of 4 signals. We have 4 kinds of hydrogen. Okay, now let's look at our carbon. Okay, so this little thing here, these are 3 peaks. That's chloroform, don't worry about it. This is a peak, this is a peak, and this is a peak. We have 3 peaks. So we have 3 kinds of carbon. What else do we know about our 3 kinds of carbon? None of them are carbonyls. One of them is probably attached to an oxygen or a halogen because it's up near 70 ppm. So we're looking for an oxygen that's not a carbonyl. Okay, so now let's look at our structures here. Right away, just from that information, we can eliminate this one and that one. Why? There's no carbonyl, but there is an OH. There's no carbonyl because our carbonyls would all be here. So we know we don't have any carbonyls. And we know we have an OH because of this peak here is a broad singlet and we don't split through oxygen or nitrogen. It could have been a nitrogen, but we don't have a nitrogen in a choice, so we'll just call it an oxygen at this point. So we have 2 choices here, okay? So now we have to figure out how many signals we're going to get for each of these, okay? We're going to look at how many carbon signals and how many hydrogen signals. I'm going to do the hydrogen signals on the top here. We're going to have 1 hydrogen signal, and these are going to be the same. Do we agree? Methyl groups attached to the same carbon with a hydrogen on it, so I think they're the same, okay? So that's going to be A, B, C, and then of course our hydrogen B. So we have 4 hydrogen peaks. So that's consistent with our proton number. Okay, how many carbon peaks do we have? We have 1, and I guess those methyl groups are again the same. 2, 3 carbon peaks. Okay, so we have 4 hydrogen peaks and 3 carbon. Oh, that didn't help. All right, let's do the next one. All right, let's do the next one. Okay, we got that. All right, we have 1 hydrogen here, 1 hydrogen here, 1 hydrogen here, and D, 1 hydrogen here. So we have 4 hydrogen peaks. Okay, let's see how many carbon peaks we have. We have 1 carbon, 2 carbons, 3 carbons. Okay, so that didn't help at all. Okay, I guess we're gonna have to look at splitting. Oh, wait. Is that right?
Wouldn't there be 5 peaks in the hydrogen?
How many hydrogen peaks do we have in that cyclo? And no. We have these hydrogens are different than these hydrogens. So actually I should draw them in a separate color. These hydrogens. This hydrogen's different than that hydrogen. And all 4 of these hydrogens are the same. So we have 1, 2, 3, 4, 5 hydrogen signal in cyclopentane. So what's our answer? The second one. Okay, now let's look what our splitting would be here, just to double check to make sure we're not crazy. Okay, we're going to have, let's see, this is going to be a doublet because there's 1 hydrogen here. This is going to be a doublet because of 1 hydrogen there. This is going to be 6 plus 2 is 8. So it's going to be 9. 9 peaks. And then this is going to be a singlet. Let's look at our proton NMR. That could be 2 or 3. That's definitely multiplet, and it's definitely odd number. And that could be a doublet. So I think that we have double checked it, and it can't be this because of the number of signals. So don't forget your rings, okay? All right, so let's do the second one. All right, so let's see what we see. Okay, so this is a quartet. This is a triplet. Ooh, this is cool. See this right here? Quartet, triplet. I can already tell we have an ethyl group hooked to an oxygen. We have an ethyl group right here. This is the C2, this is the C3, hooked to an oxygen. And then we have something that almost looks like a singlet hooked to a carbonyl. So I think that's a singlet. And so that's going to be a CH3 hooked to a carbonyl. Okay, again, I'm doing it backwards. I'm predicting what it might be from the structure. Do we see why, because it's at 4 here, this CH2, this thing that's split by 3 hydrogens, is going to be this ethyl group hooked to an oxygen. This is a common pattern. Okay. So now let's look at the carbon NMR. Oops. Right here we have 1, 2, 3, 4 signals. We have something with a carbonyl with an oxygen or an electronegative atom, something next to an oxygen, and then something next to a carbonyl, and then something far away. Okay, so let's look at our choices here. Of the choices here, can we discern it just by the proton NMR? Yes, we can, because we have the CH2, CH3 hooked to an oxygen. That's that 4, the quartet at 4 tells us we have this. So we have this, but let's double check it with our carbon NMR. We have a carbonyl next to an oxygen here. We have a carbon next to that. And then we have the CH2, no, carbon next to the carbonyl here. The CH2 next to an oxygen and the CH3. So we have the right signals. And we have a singlet here. The singlet is attached to a carbonyl. That means we have a methyl group attached to a carbonyl, and we have a methyl group attached to a carbonyl. All right. What's your confidence level on proton and carbon NMR now? 60. Oh, come on, give me a 75. Okay, so do you feel this exercise helped you? Okay, so when you go back and do the homework that you do tomorrow night, you can use this same strategy for all of those questions, and it should be not hard. You should be able to get down to 1 or 2 places, and you should make a rational decision between. Even if you're wrong, you at least talk to yourself through the system. Okay? All right, it is a little early. You got 6 minutes if you want to hang around and talk. Other than that, you can head on out. I can put empty ones on canvas. I'll put empty ones on canvas. And I'll also put the slide that you know. I thought I might get to it today, but I figured having you sit there and work through it and ask questions is more. I'm gonna get my SI to do this next time. All right, I'm gonna stop sharing, everybody, and see you later. And I did record, so I think. Let's see.